properties of matter and the changes of matter. All right, so we just talked about the types of matter. We have a pure substance versus a mixture. We can break the pure substance down to elements and compounds. We can break the mixtures down into heterogeneous and homogeneous mixtures. So those are the two different types of matter. We also have properties and changes of matter. Let me quickly go over these. The properties of matter are considered either a physical property or a chemical property. And we can say a physical property is simply when you're changing its appearance, when the substance's appearance are one, I don't mean to say change because that's a physical change. So ignore the word change. I'm saying one that displays, or one that a substance displays without changing its composition. So one that a substance displays without changing its composition. An easy example to understand would be like when the substance changes its color a lot of times, we can say that it's just a physical property. It changes, I'm sorry, I don't mean to say change, when it displays a different color, when we're describing its color is what I really am trying to say. When it's describing its color, when you're describing a substance's color, like if I describe this pen as being blue, that's a physical property of the pen. If I say, what's that?
I said odor of the gas, something like that.
Yeah. So, or if I say the way it smells, or the way it feels, or even the density of a substance is describing its physical properties. On the other hand, I can have a chemical property. And a chemical property is one that a substance displays only through changing its composition. So, with that said, the only way you can see the chemical properties is when a substance changes its composition. So for instance, if I want to say that something is flammable, or say the flammability, I'll say it's flammable, or we described its flammability. Basically, it's basically if it can catch on fire or not. The only way we can know if it catches on fire or not is after it catches on fire. So that's the difference between a chemical property and a physical property. Another example of a chemical property is toxicity and corrosiveness. Like I only know that it is corrosive after it corrodes. So, another thing, these are physical and chemical properties. We can also have changes of matter, which we then say we can have a physical change versus a chemical change. And these are just describing the substance you're talking about. The properties describe them. The changes, on the other hand, something actually changes. So changes of matter. If I have a physical change, a physical change is just when you have a change in appearance. But not composition. So if I have a change in appearance, but not its composition. So for example, let's say I have ice that melts to water. So it went from a solid to a liquid. So I'm going to say anytime you have a change of state, basically when I have solids back and forth to liquids, back and forth to gases. Anytime I have any of these changes in states, we consider those physical changes because the appearance, it went from a solid to a liquid, the appearance changed, but the composition, which is still water, doesn't change. So I'm going to say, still another example, it's just solid ice to liquid water, or just ice to water. Another example would just be when you have glass. If I take a glass bottle and I drop it on the floor and it shatters or it breaks, the appearance of the glass is different because the shape of it is all distorted, it's different, it's in little pieces, but the little pieces are still made up of just glass. So the composition of the substance doesn't change. So I'll say glass versus broken glass. So there was a change, but it wasn't, you didn't change what it was made out of. All right, so we can also have a chemical change. And a chemical change is simply another word for just saying you have a chemical reaction. Basically, what happens in a chemical reaction or a chemical change, you have a change in composition. So anytime you have a chemical reaction, an example of a chemical reaction, if we think about rusting. So let's say we think about copper rusting. If we start off with copper, it's this pretty orangish, goldish color. And then if we expose it to oxygen for too long, I'm saying O2 is oxygen. What ends up happening is that copper and that oxygen combine with one another and they form what is known as a copper oxide. And this copper oxide is that green color that copper turns when it rusts. So this is a chemical reaction that's happening when copper is exposed to air for too long, or a lot of irons that are, a lot of metals that are exposed to air for too long, they end up becoming their metal oxides, so like copper oxides and iron oxides, and that's just all rust really is. And this brings us to what is known as the law of conservation of mass. And the law of conservation of mass says that when you have matter, it can neither be created nor destroyed in a chemical reaction. So matter is neither created nor destroyed in a chemical reaction. So this is the law of conservation of mass, and all that essentially means is that if we have a chemical reaction, let's say for instance, we have a lighter, and you know the liquid that's in your lighter is considered butane, and butane is just this organic compound. You have a lighter, you got the liquid. I don't want to draw. Let's say this is the lighter that I have. You got your liquid in there. This liquid is the butane. So what happens is when you like turn the little spark, you have butane, and the spark releases, the little turn releases the butane into the air. And when the butane is released in the air and with a spark, the air has some oxygen in it. So you have butane and oxygen with some energy, which is the spark. And what ends up happening is it forms carbon dioxide and water. And these are water vapors. All of these are gases except the liquid butane. So it forms carbon dioxide gas that we can't see with our eyes. It forms the water vapors, which is a gas that we can't see with our eyes. And that's what's released every time you use a lighter. But what's really happening is, let's say we start off with, I don't know, let's say we start off with about 58 grams of the butane. Like if we were able to measure how much butane we started off with. And then we also, when it reacted with the oxygen, it was about, let's say, this is from your book, 58 grams of the butane. It reacts with the oxygen, it's about 208 grams. If we were able to measure how much carbon dioxide and water that was produced, it would actually be 176 grams of carbon dioxide and 90 grams of water. And when you add these up, you end up getting 266 grams that we start with, as well as 266 grams that we end with. So this is what this means when you say matter is not created nor destroyed. Basically, it's just rearranging itself. So the same amount of mass that you start off with, the same amount of particles and all those things, you still end up with the same amount. They're just now being rearranged. So the oxygen and the butane, they combine, they mix together, and then the atoms rearrange themselves to now form carbon dioxide and water. And when we talk about formulas and things like that later on in chapter 5, we can write these out as actual chemical reactions. All right, so now that ends us talking about matter. Do I have any questions before I keep going? All right. If I keep going, I want to talk about energy. I want to lead us into energy. So remember I said the two main components of our universe is matter and energy. So I quickly want to talk about energy. It's fascinating to me. I think energy is like magic. We can't see it, but it's out there and it works. It's really neat to me. All right, energy. Energy is just the capacity to do work. That's the simple book definition of energy. It's just the capacity to do work. When we talk about work, we're saying that work, excuse me, we're saying all work is the result of a force acting on a distance. So what this means, when we say a force acting on a distance, if I push my paper across the table, that's a force acting on a distance. Basically, if you use any type of force and move any distance, we consider that to be work. So we just talked about the law of conservation of matter. We also have what is known as the law of conservation of energy. So what do you guys think the law of conservation of energy says?
Energy can't be created or destroyed.
Exactly. That's exactly what it says. Energy is neither created nor destroyed. We're not just making it disappear. The only thing that happens with energy is just being transferred from one substance to another. So what we have to also note is that all matter has energy. And we're going to talk about the different types of energy that we have. All right, so when we talk about energy, all matter has energy. We have what is known as the total energy. And the total energy just simply says, I have the kinetic energy plus the potential energy. All right, so when we talk about kinetic energy, all we're saying is kinetic energy is the energy associated with motion. So if we have kinetic energy, basically anything that's moving has kinetic energy is what I'm saying. I'll just say an example is anything moving has kinetic energy. This pen, when I push it and it rolls across the table, it has kinetic energy. If I bounce a ball, if I drop a ball off a table, that ball has kinetic energy. If it's moving, it has kinetic energy. Now, potential energy, it's just kind of like what it sounds like. It's just the potential to have kinetic energy, you know? So it's saying this is the energy associated with position or composition. So it's the energy associated with position or composition. The way that works is we say it's a skier at the top of a mountain. So an example would say, let's say we're going skiing, we're at the top of a mountain. The skier looks down off this big mountain and it has potential to have a lot of kinetic energy because it's going to be moving really fast once it goes down that mountain. So it just kind of depends on where you're located and what you're made out of. It depends on how much potential energy you're going to have. All right. Now, when we talk about energy, we need to talk about the units of energy. Do I have any questions before I keep going? Okay, so when we talk about energy, we need to talk about the units of energy. And the units of energy, because we're going to do some energy calculations. Units of energy. And we need to know when we're actually talking about it. The SI unit of energy is what is known as a joule. It's spelled like this. It's abbreviated with a J. It is the SI unit. Other units that we see when we talk about energy are going to be calories. These are types of energy units, and we abbreviate calories with a lowercase c-a-l. We can say that 1 calorie is equal to 4.184 joules. I'm going to put a star by here. This is something you need to know. I'll say need to know. It's going to come up a lot. So that's one type of calorie. That's one type of energy. Another type is the nutritional calorie. So nutritional calorie. We abbreviate that with the uppercase C. And we say that here I'll put a star by it, it's what I'm going to do. 1 uppercase C calorie, 1 nutritional calorie is equal to 1,000 little calories. We need to know that as well. And then we have what is known as a kilowatt hour. And it's abbreviated kWh. And the kilowatt hour is basically, think about the energy that comes to your house through your ComEd bill, the energy that's being supplied like through the electricity, through the outlets in the wall and all the power in your house. They are measured in kilowatt hours. So the next time you see a ComEd bill, you can look at it and it'll tell you you've used this many kilowatt hours and this is the rate that you're being charged per kilowatt hour. All right, so the conversion for kilowatt hours that you would know is 1 kilowatt hour is equal to 3.60 times 10 to the power of 6 joules. So that's 3,600,000 joules. That's what 1 kilowatt hour is equal to.
Do we need to know that unit of, or that conversion
The kilowatt hour? No, you don't have to know the kilowatt hour. It's going to come up on your homework, so just know that you probably have to reference it, but I won't have you memorize it for a quiz or a test.
Okay, thank you.
Okay. All right. All right. So then the next thing, let's go ahead and do a unit conversion. Let's just make sure we can convert our units in energy. Let's do an example problem. Let's say, for example, I have a candy bar. It has 350 calories of nutritional energy. The question says, how many joules does it contain? All right, so let's say I have this candy bar. I want to convert it from 350 calories to joules. So, and this is nutritional energy. So if I'm talking about 350 calories of nutritional energy, that's simply saying I have nutritional calories. So that means I have big C calories. All right, so in this case, I'm going to say if I start off with 350 big C calories, that's my given, and I want to convert it to joules. What do you guys think I need to go to? What's my first step?
You need to convert to little calorie?
To little
First.
calories, exactly. All right. So I'm going to say big C calories to little C calories. The conversion's right here. 1 big C calorie equals 1,000 little calories. So 1 big C calorie, 1,000 little C calories. So I'm out of calories. The next step says I'm going to go from what, guys? What do you think I need to go to next?
To
Calories to joules.
Calories to joules. We see that. We're going to go from little c calories to joules. So I'm going to put little c calories here, joules here. And the conversion says 1 calorie equals 4.184 joules. How many sig figs do I need in my answer?
3.
3.
Are we sure?
2.
Oh.
2.
1.
2.
We need 2 sig figs, guys. Remember, there's no decimal here. So we're going to say this number is just 2 significant figures. All right, so we're going to however many sig figs we start with. In this case, it's 2. We got to end with 2 sig figs. Let's put this in our calculator. All right, if I put this in my calculator, it's going to say 350, open parentheses, 1,000 divided by 1, close parentheses, open parentheses, 4.184 divided by 1. All right, so I need 2 calories. So if I need 2 calories, what am I saying? I need 2 sig figs. If I need 2 sig figs, what's this number rounded to 2 sig figs?
1.5 times 10 to the 6th.
Perfect. Did we see this, guys? Did we say, okay, 1, 2, that's my 2 sig figs, and then I need to look to the right and round this 4 up to a 5, and then everything else after that is 0. So I can say 1.5 times 10 to the power of 6, or I can say 1,500,000. This still gives me 2 sig figs. And my answer is going to be in joules, so this is joules. All right, any questions before I keep going? All right, so these are the units of energy. Let's keep going and talk about other types of energy. Other types of energy I want to talk about, we have thermal energy. Thermal energy says it's the energy that's associated with the random motions of atoms and molecules. So atoms and molecules, they move, they vibrate, and this random motion is considered the thermal energy. When we talk about thermal energy, we say the hotter an object, the more thermal energy it contains. And this just means that when we're talking about substances and objects, that when you raise the temperature, the particles move faster, they move a little quicker, they vibrate a little bit more, and we say the hotter the substance, the more thermal energy it has. Now this brings us to temperature. Temperature all right, so temperature is just a measure of a substance's thermal energy. And basically, it's just saying how hot or cold is your substance. All right, so it's just basically saying how hot or cold a substance is when we talk about temperature. And we know that we have different temperature scales, and the different temperature scales that we're going to talk about in this class. First off, if we talk about the temperature scale that's used in the United States, we're talking about the Fahrenheit scale. And the way we abbreviate Fahrenheit, we say degrees Fahrenheit. But most of the rest of the world uses the Celsius scale. In the Celsius scale, we use the symbol degree sign and capital C. So the US uses Fahrenheit. Like if you look at the temperature outside, I'm not sure what the temperature is in Chicago, probably somewhere in the 60s or 70s. And that's measured in degrees Fahrenheit. But the SI unit is neither one of these temperature scales. The SI unit is actually called a Kelvin. And the Kelvin does not have a degree sign. It's just abbreviated with a capital K. This is the SI unit. Now, when we talk about how we go back and forth between these temperature scales, we have equations that we can use. And let's just talk about what these equations are. So the equation that we're going to use the most is going back and forth between Kelvin and Celsius. And that equation says that if you want to know the temperature in Kelvin, all you have to say is you add 273.15 plus the degrees in Celsius. The equation to go from degrees Fahrenheit to degrees Celsius, if you want to know the degrees Celsius, we'd say degrees Celsius is equal to degrees Fahrenheit minus 32 divided by 1.8.
Sorry, Professor, for Kelvin, is that 273.15 or
Yes,
273? Okay.
0.15. And if we want to know the degrees Fahrenheit, we'd say degrees Fahrenheit is equal to 1.8 times degrees Celsius plus 32. It's just basically this equation rearranged. We multiply 1.8 by both sides, and then we added 32 to both sides. This is the main one you need to know. We're going to use it the most. This will come up on the next quiz. These will come up on the next quiz. But for throughout the entire semester, this one's going to come up the most. All right, so if we keep going, let's talk about what these scales really show us, and we can then do an example problem. All right, so first off, let's just show water. This might come up. Water boils. Does anyone know what water boils in degrees Celsius?
100 degrees.
Yep, 100 degrees Celsius. It boils at 100 degrees Celsius. If we convert that to degrees Fahrenheit, meaning we just plug it into the equation. If we put 100 degrees Celsius in, multiply it times 1.8 and add 32, we're going to get 212 degrees Fahrenheit. And if we put 100 degrees Celsius into this equation, so 100 degrees Celsius plus 273.15, we're going to get 373.15 K.
Could you do that over for me? I kind of got lost there.
Okay, yeah. I'm basically saying that I'm using these equations to convert. If I take 100 degrees and plug it into this equation, so if I plug in 100 for C, and then I add 32 to it, I'm going to get 212. So 100 times 1.8 is going to give me 180, plus 32, it's going to give me 212 degrees Fahrenheit.
Okay, gotcha. Thank you.
Same thing for Kelvin. If I plug in 100 degrees here for this equation, if I add it to 273, I'm going to get 373.15. All right, so that's the temperatures in the different scales for when water boils. When water freezes, does anyone know what water freezes in degrees Celsius?
0 degrees centigrade.
0 degrees Celsius. Does anyone know off the top of their head in Fahrenheit?
32.
Yep,
Minus
32 degrees Fahrenheit. I remember this just from moving to Chicago, looking to see when it's going to snow. And then finally, if I'm converting it to Kelvin, I'm just going to plug in 0 right here, and you see that it's just going to be 273.15 K. And then I have what is known as absolute zero, meaning the coldest that we can measure, the lowest temperature. At absolute zero, this is why we use the Kelvin scale, because the Kelvin scale gives us absolute zero. So what this means is 0K is considered absolute zero. So if I say 0K, if I plug in 0 and solve for Celsius, that means I'm going to get negative 273.15 degrees Celsius. And then I plug in that negative 273.15 and solve for degrees Fahrenheit. I'm going to end up getting negative 459.7 degrees Fahrenheit.
So you're saying nothing can get colder than absolute zero?
Yeah.
Okay.
And I'll just say the Kelvin scale gives us absolute zero. All right, so let's do an example problem. It's going to come up on the quiz and the homework, doing our temperature conversions using these equations. My example says, what does my example say? My example says, let's convert negative 48 degrees Fahrenheit. Let's convert it to Kelvin. You guys spend a second and see if you can use these equations to go from degrees Fahrenheit to Kelvin. So notice that I do not have an equation that's going to convert degrees Fahrenheit to K, but I have one that goes from degrees Fahrenheit to Celsius, or Celsius to degrees Fahrenheit, and then I have one that goes from Celsius to Kelvin. So you guys spend a second and see if we can do this conversion and see if we all get the same answer. Karen, to answer your question, the easiest way to remember equations for the quiz, I would say just learn these two. So this one, I think is pretty straightforward. You just remember you're just adding Celsius to 273.15. And then this one, I would just memorize it. And if you know these two, you can easily rearrange the equation to solve for F. Some things, I can't say an easy way. I just say, just try to memorize it and practice it. You know, you do enough problems using these equations, they come to you. Okay, I see a couple of you guys have an answer. All right, let's talk it through because it looks like we're getting similar answers, but we're not sure about our sig figs. All right, let's talk it through. All right, so we understand we're going to go to what first? We're going to go to Celsius first, and then we're going to go from Celsius to Kelvin. So to do so, I know my degrees Fahrenheit, so I'm going to use that equation. I'm going to use that equation that says if I plug in the degrees Fahrenheit, I can solve for degrees Celsius. So I'm going to say -48 is my degrees Fahrenheit, minus 32 divided by 1.8.
Can you put up the paper just a bit, Professor, please?
Yeah, I was trying to show both screens.
Oh.
Both papers. Okay, so this is the first equation I'm going to use. We always have to keep up with our sig figs. So basically, we started with 2 sig figs, but the equation says we're going to subtract and then we're going to divide. But in reality, how we work this out is we're going to just say, oh, okay, if I start with 2 sig figs in this equation, I'm going to end with 2 sig figs. These are kind of like, this equation is kind of like an exact number type thing. So I'm going to go ahead and say I need to have 2 sig figs in my answer for this case. So if I have 2 sig figs in my answer, what did you guys get here? Let's not round it to the end. So just tell me what you got in your calculator.
-44.4 repeating.
-44.
All right, -44 point, I heard somebody say it.
0.4 repeating.
Yeah, 0.4 and so on and so on. So that's going to give me my degrees Celsius, but I need to make a note to myself, oh, I started with 2 sig figs. Let me stop with 2 sig figs. Okay, so this is degrees Celsius. And then the next step says I'm going to go from degrees Celsius to Kelvin. So I'm going to say, use the next equation that says, okay, just add 273.15. So I'm literally just going to add 273.15 to this, and it should give me my degrees Kelvin. But now I have to look at the sig figs again, and let's pay attention. Remember, you guys said it stopped right here with 2 sig figs. So how many decimal places is that?
2.
2.
Oh, 0.
0. Exactly, it's 0 decimal places because technically if I ended the question at degrees Celsius, that's where it would end. But I'm not going to round into the very end, so I'm going to wait, add these together. This is no decimal place, 2 decimal places. My answer should have no decimal places. And with no decimal places, what do you guys get for your answer?
230.
229.
229.
Yeah, I think it's 229, guys. 229K. I see some of us put it in the chat. You got like 228.71. That's what your calculator says, which is correct. But then we want no decimal places, so we still have to round it up to 229.
I have a question.
Mm-hmm.
So, this answer, would that not be 3 sig figs? And you said it's supposed to.
It is 3 sig figs, but remember, we are using the addition subtraction rule now.
Oh, okay.
You get what I'm saying? So this one, we just started with 2 sig figs in our answer. If the question said how many degrees Celsius, the answer would be 2 sig figs, 44. But then it said how many degrees Kelvin. Now we're adding together. When we're adding, it's no decimal place, 2 decimal place, so we need no decimal place.
Okay.
Yeah, I know it gets a little tricky. But like I said, we do it with everything. You guys will get used to it. Yes, do I have a question?
Yeah, I have a question. So at first, when I divided the -48 and then like the 32 I mean, when I subtracted that and then divided it, if I do it all together without the parentheses, I got a completely different answer. So I would need the parentheses, right?
If you said negative 48 minus 32 divided by 1.8. So let me tell you what the calculator reads this as. You do need the parentheses. The calculator is saying,
Yeah,
okay, the order of operations say we're going to multiply or divide before we add and subtract. Remember PEMDAS? So it's going to divide these 32 divided by 1.8, and then it's going to subtract it, and that's why you get a different answer. So yes, you do need the parentheses, and just remember that. So if you have an equation with a fraction, I would do what's on top first, and then do what's on bottom.
Professor, I have a question.
Mm-hmm.
So I'm a little confused. I know we talked about this before, but since you're ending in addition or subtraction,
Uh-huh.
I don't understand that part.
So remember the rule. What's the rule for addition and subtraction?
Least amount of decimal points.
All right, so we said this number stopped with 0 decimal points. This number has 2 decimal points. So we need the least amount, which is 0.
Okay, if it were to end in multiplication or division, it would be least amount of sig figs, right?
Exactly.
Okay, so since it's ending in addition and subtraction, we forget about the sig figs. We just go based on the decimal point, least amount of decimal points.
Exactly.
So we have to wait to see what we end up with then.
Yep, that's why I say just set it up as 2 different problems. You know, you get an answer, and then this is like a whole new problem and get an answer for that.
Okay.
Okay.
Thank you.
Any other questions on this? Hate this piece of cake. All right, so it is 11. Okay, let's take another break, guys. I want to talk about heat, and I promise heat is the last thing I'm going to talk about. But before I overload your mind with heat, I want to take a 10-minute break for you guys. So let's take a 10-minute break. We come back, we talk about heat. We can do some practice problems with heat and heat capacity, and that'll be it for today.
Thank you.
Okay. Let me know if you guys have questions. Miriam. All right, so when we talk about heat, heat has units of energy. Has units of energy. And we say that heat is defined as a transfer or exchange of thermal energy. And this is caused by a temperature difference. So when we're talking about the heat of the substance, we are just talking about how the thermal energy is being exchanged. All right, so we have 2 different types of processes when we talk about heat being exchanged. We have an endothermic process. And in the endothermic process, only thing that's happening is that the heat is being absorbed. Or we can say that the heat is being gained. So you're gaining heat when you have an endothermic process. If you're gaining something, we're going to say it has a positive sign. It's like you're gaining, you're adding money, you're gaining money. We're going to have a positive sign behind it. And when you are versus an exothermic process, an exothermic process is saying that heat is being released. Another way of saying heat is being released is we can say heat is being emitted. Or we can say heat is being given off. And we say we're losing heat in all these instances. All these cases, we're losing heat. And when you're losing heat, we're going to say you have a negative sign associated with it. Now, when we talk about the symbol for heat, the symbol for heat is abbreviated with the lowercase letter q. All right, so we can also measure something that is known as a substance's heat capacity, which is important. Heat capacity. And the heat capacity is just the quantity of heat. And remember, heat has units of energy. So most of the time when we talk about heat, it's going to be in units of joules. So the quantity of heat, and I'll say in joules, just so it's clear, required to change the temperature of a given amount of substance by 1 degree Celsius.
Professor, can you give us example for endothermic and exothermic process?
Oh, yeah. So when we talk about exothermic versus endothermic, an exothermic process or reaction is mostly when we're going to talk about when you have exothermic reactions. Exothermic is just saying, like, for instance, something catches on fire. You know, it's going to give off some heat. It's going to be hot when we talk about exothermic reactions. Endothermic reactions are kind of like the opposite. You're going to be gaining heat. So let me think of a good example that's everyday. Let me think of one the book gives. What's the book give us? Usually when we have, here it is. What's the book give us? Yeah, okay. Changes in state. Changes in state are good examples of endothermic process. So for instance, like when ice melts, like when you're changing from a solid to a liquid, when ice melts, what ends up happening is that it absorbs heat from the surroundings. So basically the ice melts in the glass and it cools the water down as the melting ice absorbs the heat from the water. So that's how you think of like an endothermic process versus an exothermic process. When we get to chemical reactions in chapters like 5, 6, and 7, we're gonna see a lot of reactions that are endothermic versus exothermic. I don't want to bring them up too much to confuse you, but an easy one for exothermic is just like anytime anything catches on fire, you're going to release some heat. It's going to give off some heat. Okay. So
How about like ice melting? Is it endothermic or?
yeah,
exothermic?
I'm saying that's endothermic when you're saying ice is melting.
Thank you.
All right. So if I bring it back to heat capacity, like I said, the heat capacity is just saying the quantity of heat required to change the temperature of a given amount of substance by 1 degree Celsius. We can also talk about the specific heat capacity. And the specific heat capacity, it's just saying it's the same thing, but the specific heat capacity, we're going to abbreviate it. The symbol for it is going to be the letter C, the capital letter C. A lot of times you'll see it written just simply as S.H, like specific heat. But C is the actual symbol for specific heat capacity. And it's the same thing. It's just saying that when you have this given amount, when that given amount is measured in grams. So all this is really saying is how much heat or how much energy is required to make your temperature go up by 1 degree Celsius. Now to figure that out, we can use an equation, and we can say the equation for the specific heat capacity is the one we're really going to care about. The equation for specific heat capacity says that C is equal to the amount of heat, which is Q, divided by the mass times the change in temperature. Now, some stars that I want to write out is, first off, when we talk about the specific heat capacity of water, C of water, just like we have to know the density of water is 1 gram per milliliter, we got to know the specific heat capacity of water is going to be 4.184 joules per gram degrees Celsius. This is 1 unit. This whole entire thing is 1 unit. Joules is for the heat. Grams is for the mass. Degrees Celsius is for the change in temperature. So let me write out what all this means. So in this case, when we talk about this equation, do I hear a question?
Yeah, what does the triangle mean?
I'm going to tell you. So C, remember C stands for specific heat capacity. Specific heat capacity is one of those measurements like density, where it doesn't matter how much of a substance you have, the specific heat capacity of that substance is always going to be the same. Q stands for heat, and the Q is measured in joules or calories most of the time. So I'll say joules or calories. The specific heat capacity is going to have units of joules per gram degrees Celsius or calories per gram degrees Celsius. But most of the time in this class, we're going to use the J over G degrees Celsius. The M stands for the mass, and the mass is going to be in grams, which is just G. And then the change in temperature, this triangle T, the change in temperature. Anytime you see this triangle sign in front of any variable, that just means you take that variable's final and you subtract it from its initial.
Sorry,
So,
Professor, you said the temperature's final?
no, I'm saying that the triangle T stands for the final temperature minus the initial temperature.
Okay.
So triangle anything means final minus initial. That's all I'm saying. And this is still going to be in degrees Celsius. This has units of degrees Celsius. All right, so let's talk through it again. I'm saying the specific heat capacity, which is in units of joules. Let's say it's just joules is equal to, sorry, it's joules per gram degrees Celsius, is equal to the heat, which is Q, which is in units of joules, the mass, which is in units of grams, and the change in temperature, which is in units of degrees Celsius. So that's how you get this unit, joules over grams over degrees Celsius. And let's do an example problem. And let me give you an example to show what I'm really talking about. So it's basically saying, how much energy does it take to change the temperature of a substance by 1 degree Celsius? Now, I'm going to give you some specific heat capacities. We know the specific heat capacity of water is the 4.184, but the specific heat capacities of a lot of other substances are pretty low. I think there's a table in your book. Let's see what page that table is on. That table is okay, the table is on page 76 in my book, so maybe it's 75 or 77. It's table 3.4, specific heat capacities of some common substances. You guys might need to know this for your homework. You can easily just Google, you know, specific heat capacities of common substances. But what this looks like is it's just saying, you notice that most of the other substances have a really low specific heat capacity. And water has this really high one at 4.184. So what this is really saying is that when we think about the specific heat capacity of water compared to other substances, is that it takes a lot of energy to change the temperature of water by 1 degree Celsius. And that's all we're usually trying to calculate, the amount of energy it takes to change the temperature of a substance by 1 degree Celsius. So let's think about when we are in Chicago. Like if I was in Chicago right now, maybe it'll be warm by my house. I don't live next to the lake. I don't live too far from it, but I don't live right next to the lake. So by my house, I don't know what the temperature for Chicago says. Let's say if I look at this, because this happens to me all the time. If I look at the weather, the temperature says it's 63 degrees in Chicago right now. So maybe it's 63 degrees by my house. If I then go downtown and I'm like, oh, it's not that cold, you know, like I don't need anything. I should be okay, maybe a light sweater. But if I go downtown by the lake and I get downtown and I'm like, oh my gosh, it's so much colder than I thought it was going to be. Has that ever happened to any of you guys?
Yeah.
Yeah. You guys know what I'm saying? It's like you go downtown and you're like, shucks, I'm freezing. So the main issue that happens is because you're by this big body of water, which is Lake Michigan. And in Lake Michigan, to change or increase the temperature of Lake Michigan, it takes a lot of energy. It takes a lot of energy to change the temperature of Lake Michigan. So, you know, it's just like, you know, we think about putting trying to boil a pot of water. It's like, it doesn't boil right away. It usually takes like 10 or 15 minutes to boil your water. And that's because it takes a lot of energy to change the temperature of your water. So that's really all these specific heat capacities are saying. They're just like, how much energy is it taking to change the temperature of your water or any substance you're trying to measure? So when we think about these example problems, let's do an example problem really quickly and then we can wrap up. An example problem says, let's calculate the amount of heat required to raise the temperature of a 65-gram sample of water. From 32 degrees Celsius to 65 degrees Celsius. All right, so this is what the question says. Let's calculate the amount of heat required to raise the temperature of 65 grams of water from 32 degrees Celsius to 65 degrees Celsius. So I want to raise the temperature of this water 30 degrees. That's a lot. Now, I know that I have the equation that I just talked to you guys about, saying that the specific heat capacity is equal to the amount of heat divided by the mass times the change in temperature. In this case, we are looking to calculate the amount of heat. So can you guys tell me which letter is the amount of heat? Which variable?
Q.
What is it? Q. All right, so we have to recognize that heat is Q, so I'm looking for Q. So if I'm looking for Q, I need to rearrange this equation to solve for Q. If I rearrange this equation to solve for Q, it's going to say Q equals
M times C times
T times N times the change of T.
times M times difference temperature.
right. We get that. This is what it's going to say Q is equal to. We just multiplied both sides by mass and change in temperature. So in this case, we just have to plug everything in. We're looking for Q. Can anyone tell me what my C is? I know it's specific heat capacity, but we're talking about water. What's the specific heat capacity of water going to be?
4.184.
4.184, and then we're going to say joules per gram degrees Celsius. What's my mass going to be?
65 grams.
Grams.
65 grams. And then my change in temperature, remember that triangle
Right.
T just simply means I'm saying my final temperature. What's my final temperature?
65.
65 degrees Celsius. What's my initial temperature?
32.
32 degrees Celsius. This is how you calculate your change in temperature. All right, so we're still going to go through the order of operations. We're still going to do PEMDAS. We're going to do the parentheses first. We're going to go through the rules of SIGFIG rules. Remember, subtraction says least decimal places. There's no decimal places in both of these numbers, so my answer should have no decimal places. What's 65 minus 32?
33.
33 degrees Celsius. And then I'm going to multiply times 2 sig figs. And then this is an exact number, so I do not have to worry about the sig figs and the 4.184. So you guys tell me, how many sig figs should I have in my answer?
2.
2. We see that we should have 2 sig figs in our answer. What's our answer with 2 sig figs? Or would you guys get in a calculator before you even think about the sig figs? What's a sig fig say? I mean, what's a calculator say?
8974.68.
68.
So it says 8974 point what?
68.
68.
68, and this is going to be
9.
units of what, guys? What's my units?
Joule.
Say it again.
Joules over grams in Celsius.
Try again. We're just looking for heat. Remember, we're just
Joules.
looking for heat.
Joules?
Just joules, because look, the grams cancel out, the degrees Celsius cancel out. We're just
Oh.
joules. So in this case, you guys said I need 2 sig figs. 1, 2. Look to the right. Round up or down, guys.
Up.
We're gonna round up. So if we round this
90.
number up,
90.
we're gonna say
9.0.
9, 0, and then 0, 0. But that's not 2 sig figs. That's only 1 sig fig. So how can I write this number in 2 sig figs?
9.0
9.0 times 10 to the 4th.
There we go. 9.0 times 10 to the power of,
third.
yeah,
Three.
thanks. I'm just listening. Times 10 to the power of 3 joules. Do we see that? This is an example of where you'd have to write your answer in scientific notation to express the correct number of sig figs. If you put 9,000, that's only 1 sig fig, you probably lose a point. If you put 90, that's just not correct at all. I'd still probably only take off a point, but you need to make sure that we know, that's why it's important to understand how to write it in scientific notation. Okay?